So MIPT, Moscow Institute of Physics and Technologies. For our guests, it's, in my opinion, very strong university for doing physics and mathematics. And I'm very glad that we have very nice students there. And another organization that I'm also representing is the Russian Quantum Center. So Russian Quantum Center is maybe not so well known among the audience, but first of all, it is supporting this conference already 2 years. So I'm very glad that they're doing this, and I'm very like this event. And just few words about Russian Quantum Centers. It started as an idea from 2010, I think, and then it became realization. And then now it's more than 600 employees, around 20 scientific groups, and also 5 commercial spin-offs. So they're doing experimental science, also theoretic science. Okay, so I will move further. So this is the representation of my lab that I'm working in and heading. So mostly we are dealing with light and magnetism. We want to use light to modify magnetic properties of material or vice versa. We use magnetism to change the optical, for example, properties of materials. We study the modification of optical properties in nanoscale materials. We also perform the manipulation of the magnetic order with femtosecond light. Basically, we deal a lot of experimental studies. And from the practical standpoint, I think I named just few of them. So we are studying 1D materials for single photon sources. Mainly, this is single-wall carbon nanotubes. Also, we have recently we obtained the terahertz source, femtosecond terahertz source for with very intensity field like 800 kilovolts per centimeter, and we have this set up on the table, optical table, so we can use this excitation for time domain spectroscopy or any other experiments for this time kind. And also we are dealing a lot with 2D materials for the topics of the quantum simulation and photo detection. And exactly today I will tell you the whole talk will be about 2D materials and the experimental implementation. How is it to work with 2D materials? Yeah, I think we move further. So the outline of the talk is the so-called, I call it evolution of twistronics. So there is a field which is called twistronics when you have two, for example, monolayers of two-dimensional materials, and then you put them on top of each other with some specific twist, and this twist allows you to obtain some different properties. And the whole talk I will show you these things. So we will move from the specific so-called magic angle of graphene. It is around 1.1 degrees. To the more flexible and robust properties found in another type of 2D materials, transitional metal decalcogonides, where this so-called magic angle can be broader. So not only 1.1 degrees, but it's from 0 to 4 degrees. Maybe for you it makes not much difference, but in the experimental realization, it is rather important, because for graphene, if you want to find out this magic angle and this physics and this unique properties, you really need to struggle hard to make this 1.1 degrees, and then when you put them on 1.1 degrees, specifically it might twist a bit, and at the result you will not get this physics that you're expecting, and then you need to make like 20 samples to demonstrate it is working. So the key advantage of using another type of materials is because they have the massive fermions, and they allow this bandwidth quenching without fine-tuning, and yeah, this we will discuss. And the scope of this presentation also some sort of fabrication mechanics behind this process, some models that I use to describe this area, continuum Hamiltonians, and maybe just few applications I will also be able to demonstrate. So from the theoreticians contests, unlike graphene, where the flat bands arise from precise destructive interference of the Dirac velocity, in this TMDC, these flat bands, they arise because of the bandwidth quenching. So, and the large effective mass lowers the kinetic scale, energy scale, and allows to these shallow potentials trap the allows to trap the carriers effectively and to demonstrate this physics. So if someone does not understand anything from the bottom sentence, the whole lecture, I will describe everything in more detail, so don't be afraid. Yeah, so this is the introduction of graphene. I'm sure everyone knows this graphene, very important, Nobel Prize winners also from MIPT. And in my opinion, there are few properties that are important. So first of all, this platform allowed to make the fundamental studies, to study the physics and to demonstrate experimentally that these theories, they were real. Then the graphene has some sort of peculiar properties that are very interesting, and advantages from my point of view and why it got very popular is because it's rather easy to make it in the lab. We will also discuss why it is so. Because it is flat, it is easy to integrate it for applications. So basically it's rather flat. You can put it on top of any substrate and then you try to find these extra features because of interaction of 2D material with something else. And there are different applications because of this. So because it's flat, it's easy to integrate into some commercial products, some sort. Yeah, and this is the representation. How is it so that you can see graphene in the transmission electron microscope? But I mentioned that it is very easy to make it in the lab, and one of the important things that it is possible to find it basically with your eye or using just simple optical microscope. But this is very important because you are studying the monolayer, so it's single atom layer, but you can see it with your eyes in the optical microscopy, and that's why it is a lot of people decided, okay, we can do it in our lab. And basically you, I suppose, all know that you can have this Scotch tape technique, and then you can, with the Scotch, obtain monolayer graphene, let's say quantum material. Yeah, and why is it so? Because, for example, it was described in 2007 that simply by looking at the optical microscopic contrast, you can see these flakes. So sometimes you cannot see it, but sometimes you can easily see something. Yeah, so I'm struggling with this thing. So in this left image here, you see that there is some faint contrast, and you basically can tell where you have mono or few layers and so on. And the people who are doing this by their hands, just in the lab, they can, when they use the very same substrate, it is very important, when they use the very same material, and they can simply, by looking in the optical microscopy, they can tell you whether you have single layer or two layers. So the person who is really doing this, he will easily tell you. Yeah, and here you see there are different wave numbers and different contrasts. So depending on the wavelength and the contrast, you can easily see or not see the material. And it is very well explained. So it's called the wave optics of atomic layers. So basically what is happening, you are just direct imaging of the monolayers. Here's the specific, like just the usual experiment. So you have a monolayer. Let's say here it's then transition TMDC, but it doesn't matter. Then you have a substrate and the silicon substrate and the electric between this. So depending on this width, thickness of this dielectric, you have different optical contrast. So it can be described easily. So the substrate has specific n values, then the monolayer has its own complex refractive index. Then you can evaluate the optical contrast depending on the substrate and the sample. And it turns out that the substrate acts as a resonant cavity. So depending on these values, you either can see your material or cannot with a bare eye. Yeah. Just a few words about this complex refractive index. I will not talk about this anymore in the presentation, but I think it's important to stress out that different layered materials, different van der Waals materials, they have different complex refractive index, and a lot of studies that demonstrate there are different interesting properties like anisotropy and so on of the different orders. And basically people in MIPT, in the Center of 2D Materials and Photonics, where our lab is, they are studying these materials with ellipsometry, so they can directly evaluate N and K parameters, and they made lots of works demonstrating that indeed for some materials you have anisotropy, for some not, and in some cases they have really huge values for these parameters. Okay, moving further. So how is it happening exactly? So you have the Frenzel interference mechanism. and you can calculate it like with this formula. There is a phase shift that depends on the N2 value of the dielectric, and then the width of this dielectric of this oxide. So you can basically purchase this substrate with different values of the electric of this CO2, and this determines the interference condition. So it started that for some specific thickness, let's say 285, it's very easy to see the refractivity around 500, where our eye is very sensitive to the changes. Yeah, okay. Moving further. So another thing is, you all heard this Scotch tape technique. So as I mentioned, everyone can purchase Scotch, purchase this, let's say, pencil, yeah, and then use Scotch tape. And then on those different sides, you have maybe, if you repeat it many times, then you will find that in some spaces there can be like a monolayer, and then you stick this Scotch to the substrate you are using, and then you deattach it. And in some case, this monolayer might stick to the substrate, and then you will have on the substrate you have a monolayer 2D material. Yeah, this everyone knows, but then there is some sort of extra things that need to be done in order to use these things. So what people are doing, they use this so-called tear and stack process. So they have the polymer step. So yeah, there is a flake, there is your flake of your interest, and then you put your polymer on top, and there is depending on the speed how you deattach this polymer. So you must have the ability to touch the 2D material and the ability to remove it away from the material with your, let's say, polymer stamp. And depending on so here are the formulas. I know the formulas are very important. So here I try to introduce as much formulas as possible. So the dependence of the adhesion energy to the velocity. So it turns out that there is some specific value, and it depends also on the speed how you remove it. So depending how fast you do it, you can either tear off the substrate from the sample, the 2D material from the substrate, or it will be still there. So you must play with these parameters like speed of the deattaching and everything, and then you can obtain your material on the stamp. And then you will ask me, so why to do it? And the reason is the following, that it turned out already in this review in 2013 that you can have different 2D materials and put them on top of each other. Because they are flat, it is you can put them on top, and because they're interacting with the van der Waals forces, so you can deattach it. So van der Waals forces is very important because it is not very strong, and you can, with these stamps, I don't know, Scotch and so on, you can tear off the bulk material to get to the monolayer limit. And then when you have different types of flakes, you can put them on top of each other and play with the properties. Just one thing to mention here, I will just go one slide back. That so it's written why Scotch tape graphene is important. It's important because, well, basically, if you want to obtain a very clean sample, if you want to have the monodomain thing, so you must use, unfortunately, this handmade polymer thing. So exactly this is what's happening still now in the lab. So if you want to have a very nice device, if you want to study new physics, a very clean phenomena, something very peculiar, you still need to do your material by hand, unfortunately. So people are trying to grow it in the large scale, monodomain regime and so on, monocrystals. Indeed, they have progressed in this, but so because if you want to have this applied to some applications, you cannot do everything by hand because it won't be reproducible. But the truth is that if you want to study new, like clean samples, some interesting physics, still people are using this type of devices. So they will be rather small, 10 to 10 microns and so on, but still should be done by hand. Yeah, okay, so we mentioned this was the case already, very important in 2013. And in the lab, it might look simply like this. So you have a microscope, and then there are some specific stages that can touch each other, and you can put one on top of another, and then you have something weird like this. So this is the optical image in the microscope, where you have different things of these 2D materials stacked on top of each other. For some reason, we will discuss why you need it. Yeah, and just to create these heterostructures, we discussed about this stamp that the polymer might put down things. It might stick it up, and then you need so-called the glass transition of this polymer. So you change the temperatures of your polymer, and in some point it is in the solid state, it can stick, and then you can heat it up, increase the temperature, go over the glass transition, and then the polymer melts off the flake, and you can put your flake to your desired position. Yeah, so quite easy. So there are three processes. First, there is a thermodynamics. The process relies on the glass transition. Then you need to release with this slow speed of detaching and temperatures. And then with this, you can deterministically place your 2D material on top of another thing in the place where you want. And then you repeat this many times, and you can make this like a stack of different layers. And that's also important that you reduce the heterostrain. It's very important because when you study physics in these layered materials, it all depends on the lattice that you have in your material. So depending on this lattice, and if it is banded, then the properties of the whole structure will be very different. Yeah, so now we're going, so what happened next in science was the following, that people knew how to do it. Yeah, they demonstrate everything worked, but then they demonstrated that very interesting physics in 2018. They published that, it's Nature 2018, that indeed you can even have the superconductor or mott insulating state within one device, yeah, in graphene. Twisted bilayer graphene, rotated at some magic angle, and then people demonstrated that something weird is going on there, and they can demonstrate metal mott insulated state of semiconductor. So why is it so? And I will describe in few slides further. So the main thing is that when you put one layer on top of another, you can indeed have this more potential. You see this different super lattice that is forming there. And the superlattice, the period of the superlattice is, let's say, 10 nanometers, while in graphene, the value is just below 1 nanometer, below 1 angstrom. Yeah, and the electronic structure changes completely. Yeah, so in the single layer, monolayer graphene, you can describe it like this. So this is the reciprocal space and the normal space. Reciprocal lattice here, so there are some values, and then it's very well described in the, I think everyone knows, in tight binding approach. So from the tight binding approach, you can obtain the this dependence. So basically you can describe the dispersion, and dispersion looks like this. So there are different valence band and conduction band attaching each other in one point, in the K and K prime points. Here the K and K prime points, and then there is a linear dispersion around these low energies. And basically when you study your physics, when the game Novosov, they obtained the Nobel Prize, they were studying the physics that is happening around this, in this regime, in the linear dispersion. So you have the very fast speed of charge carriers there, and the Hamiltonian can be represented by the sum of two direct Hamiltonians, which look like this. Yeah, but you see that the image of the 2D layered stack, it's completely different. There are not so much linear things, linear dispersion, and something weird is happening. So the reason for that can be the following. So yeah, just regarding the Moir pattern, is that overlapping two different periodic structures create the super period Moir potential. And you see that when you rotate this angle, you can have different, so it depends on the angle. And basically, if you have the layers of the very same, so if you have one graphene and another layer is also graphene, so if the materials are the same, the formula is like this. So it's atomic lattice divided in just by the angle, and the scale separation in this case, you see it's around 10 nanometers, and the atomic scale is like 3 angstrom. But if you have the two different type of materials, if you are making the heterostructure, it will also depend on this extra value of the mismatch of the lattice constants. Yeah. So by changing the angle or just choosing the materials with some specific atomic lattices, you can create your new length scale of your new artificial crystal. Yeah. And you can control it just by angles. So what happens next, if you take the graphene twisted structure, so it may form the triangular Mohr pattern with the lattice constant, as we discussed, depend on the angle. And also the smaller the angle of rotation, so the longer the modulation period. And in real space, you see that there are different areas. So that's so-called AA and AB stacking. So in the case of AA, they are just atoms on top of each other. And in the AB state, it is more, it's just low, energetically more favorable case, so-called the parallel stacking. So this more potential making this type of things. And you see that there are large areas, triangular areas, where there is a stacking like this, and just few points where the stacking is like this kind of. So there is a physical deformation to maximize the real area of this domain. So when you put one on top of each other, then in real life, this domains, they will form a little bit more, so they will organize themselves. So these areas with low potential energy, they will be larger. Yeah, and then we need to discuss what happens with the electronic structure in this thing. So, yeah, so there is a small, more brilliant zone. It emerges in the reciprocal space, and the length scale, it's very important. In the 1 degree of rotation, there are like 10,000 atoms there. So you can, so the electronic wave function, it delocalizes over a mini lattice. So here are the blue and red six. Anyway, so the blue and red, you see when you twist one on top of each other, this K point moves to another place, and then they form this mini band, so-called mini band. And if you make the cut like this from K1 to K2, you can obtain this image. Yeah, so there is one cone, linear dispersion, as we discussed in the monolayer regime, and another cone nearby. And then if you, so they see each other, and there is this overlap here. Sorry. And there's two landscapes. So one is depending just on this value and multiply the Fermi velocity, this the angle of the slope. And there's another thing that is two value here. Okay, so so in the theoretical framework, it is described by the continuum model. So this is called the BM continuum model. And there are a few slides that everyone will be very comfortable with. So first of all, in order to make this continuum model, so it's a theoretical framework description of the twisted graphene. So first of all, you take the Hamiltonian in single layer, yeah, and there's a Fermi velocity very high, this linear dispersion, and so on. Then you have if they are rotated by this theta degrees, so one is described plus minus theta divided by half. So this model, it works in the limit where the momentum mismatch between the direct cones of the two layers is depicted like this, and it is very small, but not negligible. So the total Hamiltonian looks like this. So there is, first of all, the Hamiltonians of the single monolayers, 1 and 2, and then there is the matrices that encode sublattice structure of the hopping. So this parameter here, which I tried to display here, so this is the tunneling amplitude between A and B sublattices, and the tunneling amplitude of between A and A. So as I mentioned, this A and A, it's more, the value is, so there's a little bit different values, like 80 millielectron volts and 110 between them. So yeah, so this is important. So because this is energetically not the very same. Yeah, sorry. Anyway, moving forward. And it turns out that there is a competition between intralayer kinetic energy and interlayer tunneling energy. Yes, so there is competition between these two things, and there is a coupling parameter alpha that can be described like this. And it turns out that there is you can talk about the renormalized Fermi velocity. at direct point scales. And this all depends also on this alpha. So you have the interplay between kinetic energy and tunneling energy. Yeah, and it turns out that at the so-called first magic angle, around 1 degrees, when you rotate one angle on top of another with specifically at 1 degrees, so this renormalized velocity drops to 0, yeah, in these areas. And there is a flattening of the band. So due to some specific interference effect, where the wave function becomes coherent superposition of layer 1 and layer 2, and the opposite group velocities, they diffract, and then the resulting standing spin wave appears, and there is no propagation. So in the image, it looks like this. So there is an angle changing, and you can see how the dispersion is changing. And when you reach this theta angle around 1 degree, yeah, like this, you see the flattening of the band around the 0 electron volts. And then if you move further, there are second magic angle and so on. So it's more complicated there. But the main thing is that by changing the angle between the layers, you can obtain the not linear dispersion, but this flat bands, but they happen due to the interference between all these things, which I explained here on the left. Yeah, here are some few words regarding this coupling parameter and different degrees depending on the angle. So you change the angle and you have the different regimes. So it's so called weak coupling, magic angle, and strong coupling. And when it's weak coupling, as I mentioned, there is decoupled layers, but in the magic angle, you can obtain this another electronic behavior, and you are expecting to see the correlated states and flat bands. And this is exactly what people demonstrate when they have the superconductors and mod insulator states in this regime. Yeah, so this is the proof. Okay, so but you see in this image there are different values, like temperature, also N somehow is varied, and you can ask, so how to do this? Yeah, I think this is yeah. So what you have, for example, you make the structure with some rotated angle, yeah, and you know that the electronic structure in this device will be like on the left side or the left hand side. But then you see you need to modify you need to get to some areas with different N values. So you just need to cruise around this area just to get to the place where you want with some specific energy. So you can be in the superconducting state or somewhere else. And in order to do it, people demonstrate that they can use electrostatic gating. So they can change the carrier density or filling factor, and they can obtain this diagram. Yeah, so you can sweep through the entire phase diagram in a single device. And this is the image how they demonstrated in their work back in the day. Yeah, I will just tell a few slides to relax that what we are doing. One of the directions is the twisted bilayer graphene. So this magic angle graphene that can be used as a photodetector. So just from the even from fundamental point of view, it will be interesting to know what happens, how the structure will detect light in these different regimes when they're in the correlated states or not. Yeah. In general, graphene is used for photodetection. It is used for photo detection for some reasons. First of all, it indeed can absorb light. You know that single monolayer graphene is absorbed 2.3%, even monolayer graphene, which is quite large for the monolayer material. And it absorbs in the broad spectral range, like let's say everywhere it absorbs the same almost. Yeah, but why people are using graphene for photo detection is not because it's absorbing everywhere, but because the temperature for which the electrons are heating up is very large. So because of this can be very sensitive detector. And we try to study what happens if we shine light on this material, on this device, when you excite it at 6 microns. And it turned out that the origin of the photo detection was quite different. And this is what we're also studying in our work. So sample dimensions are really small, let's say 3.21 micron, and we excite externally from with 6 microns. So this experimental thing, I will not disturb you much. Just in order to detect, we use the cryostat, optical cryostat. Everything is inside, and then we can have this contacts and so on, and we shine through the cryostat and detect what's going on. And yeah, this is important image. So you can see that. So for example, we have this in the cryostat, and we measure. We can measure the resistance depending on the gating. Yeah, when we change the gate voltage, we change the carrier as in the setup, and then we can get to the different fillings, and we see that here it's around 0 is called charge neutrality point, and here are some specific increase of the resistance in this 4 fillings of the more potential. So we get these correlated states, and we can move back and forth with changing the gate, and then we study the photovoltage, what happens with the photovoltage. And it turned out that indeed something is happening in these areas where you can reach the correlated state. And usually the mechanisms for the photovoltage generation are the following. So it's the photothermoelectric effect or photovoltaic effect. So in the photothermoelectric, you have photovoltage due to Seebeck effect. And as I mentioned, this delta T for graphene samples is very high. That's why the photovoltage is large. Well, that's why people are studying this. And another effect is photovoltaic effect, the generation of bias current due to the intrinsic properties of the sample. And it turned out, I think, I don't have much time, that it turned out that in our setup, it is not the photothermoelectric effect that is responsible for the detection, but the photovoltaic. And basically this we tried to demonstrate, prove that this is the case. This can be proved by the dependence on the position of your light source. Then we do some experimental studies. We change the beam position. We go around and find out that probably the dependence due to the photothermoelectric effect. So the bulk photovoltaic effect is called bulk photovoltaic effect. This is the origin of the detection in this type of devices. Well, this work is just still going on. And there is a maximum photosensitivity value of 40 milliampere per watt for circular polarization. Okay, I move further. So as you well know, there are different 2D materials, not only graphene, which we described, but vast amount of materials. Graphene, let's say, so valence band and conduction touching each other in one point. There are also TMDC materials, transitional metal decoorganized, which are semiconductors, and there is a band gap there. So it's around 1 to 3 electron volts. Also, hexagonal boron nitride, which is also very important. It's using for insulating, and the band gap is around 6 electron volts. So I'm sure that there will be further talks on this topic. I will not discuss much. I will just briefly mention what is the TMDC. It's called transitional metal dicoagonites. So they're metal and 2 dicoagonites in the structure. So the layer will look like this. So metal in the middle, and then there are 2 dicoagonites on top and below. And very important thing regarding the optical properties is the following, that when you go to the monolayer regime, it becomes the direct bandgap semiconductor, which means that you can use this for optics and for different optical properties materials if you study this one monolayer thing. So there's a very nice review by Mikhail Glazov and co-workers that are discussing the mechanisms, what's going on, how the light interacts with the material. Very interesting. So the only thing to remember is that it had direct band gap in the monolayer regime. And then you can guess, so what happens if we if you make a more potential with these 2 TMDCs, yes? So and the difference is huge because so this is the semiconductor with a large band gap. So physics occurs at the valence band edge near the K point. And there, instead of this carriers with very high speed, massless like in graphene, in this case, their masses are huge, and they obtain some strong spin-orbit coupling. And the band dispersion, it looks like this, yeah? So not the dispersion in case of graphene. And yeah, let's move further. Yeah, so also very important that because the monolayer, it lacks of the inversion symmetry, you can have the spin index to the Valley index. I will not go to details, but the important thing that we discussed how the it's described this continuum model, the McDonald model for graphene, but for the TMDCs, it's different. It's called already Wu-McDonald continuum model, and the Hamiltonian looks like this. And there are, you see some extra features appeared. Also, the band dispersion completely different. So there is intralayer more potential, a scalar potential experienced by holes in each layer. And also there is interlayer tunneling, a complex scalar field that the tunneling between the layers. So yeah, so the more potential is a direct consequence of local stacking energy. And just few words regarding the Hamiltonian. So once again, it looks like this. Different potential I explained in this lowest harmonic approximation. And the tunneling term is described like this. So important thing is that first of all, Hamiltonian looks like this. There is a tunneling parts, there is a interlayer and interlayer things, and also when you put one on top of each other, you see in this case you already have these metal ions and chalcogenides, and then there is some areas with lower energy potential and with larger energy potential. So in this, so you put one layer on top of another, then there is a metal ion, metal atoms and dehydrogenase. When the metal on top of metal, then there is a high energy and large layer separation. When the energy is minimum, when the metal on top of a chalcogen atom. Yeah, so you form this sort of potential, very deep potential compared to graphene case. Yeah, looks like this. So you have very deep potential and there is some sort of a tunneling barrier between them. So the carriers, it's difficult to hop from one side to another. And since the potential is much larger, then let's see how it goes. Yeah, since the potential is much larger, then it is more energetically difficult to get from one side to another. Therefore, this angle of twists can be much larger. So I will describe a little bit more details. So the key parameters are the following: the potential amplitude, potential phase, and the tunneling strains. And here the comparison for two type of material, molybdenum telluride 2 or WSE2. And the effective masses are different for these two materials. Then the potential is different. And you see that when you have a heavier mass, it follows stronger correlation. Yes. And because there are deeper potential wells. Yeah. And this ratio between this one, it controls bandwidth at topology. So you can play with angles, with materials, and you define what is the tunneling barriers and what are the energy potential. And here's the comparison between the twisted bilayer case and twisted TMDC. So here's the following. I mentioned that there are massless Dirac fermions in the bilayer graphene. And it requires very fine-tuned destructive interference, and it happens around this 1.1 angle of rotation. It's very difficult to obtain it. And in the case of twisted TMDCs, the reason for this deep potential is the massive fermions, and the deep potential, they also quench the kinetic energies, but this so-called magic range is much larger in degrees. So it's easier to make it in the lab and easier to find out unique properties. Here's some comparison in another regime. So this is dependence of the bandwidth on the twisted angles. So with the larger amount of twisted angles, you can obtain these values. Yeah, and it turns out that the TMDCs, they provide a highly tunable Hamiltonian. So for twisted WSE2, you see the flat bandwidth is below 1 millielectron volts, while the gap is around 3.7 millielectron volts. Okay, I move forward. So I mentioned here that twisted TMDCs, they provide a highly tunable Hamiltonian. Very important that these structures, they can be described by the Hubbard model. So the Hubbard model, it basically has two terms: the kinetic energy of electrons, which is around 1 to 10 millielectron volts, and you have a potential electron energy, which is in this case is around 100 millielectron volts. And by rotating the angles, you can modify the kinetic energy, and by changing the gating, you can modify the potential electron energy. So in your material, when you have your stacked layers, you can obtain different Hamiltonians, they can be described by the Hubbard model. And you can control over the simulator by applying electric field or filling the states. And you can change the angles between two layers, temperature, deformation, and materials. So in order to control these two parameters. And already in 2021, it has been demonstrated that there can be different Hamiltonians realized, different lattices, and different models can be realized in this stacked 2D materials case. You can see here. And in case of, just one thing, in order to cruise along this different Hamiltonians, as I mentioned, you can make the gating, but in real time, this gating should be done in more sophisticated way. So you must have basically the two gates, top gate and the bottom gate. So so this is the representation how the device would look like. So you have your Moore structure in the middle, and then you have to have the electrics on top and below, and you have top gate and the bottom gate. And while having this, you can change the so-called displacement field. It's the perpendicular electric field applied across the layers. So it can be used to independently tune the bandwidths and the gaps. So this dual control, it allows you to change either the density of the carriers when you change the sum of the gate voltages, top and bottom, or you can use the displacement, or you can change the displacement field, which is controlled by also top and back. So you can selectively change the filling factor and so on. It is very important in order to easily follow what's going on in your structure, you must have these several gates in order to change the displacement field. Oh yeah, one more thing to mention regarding the experimental realization. So you must somehow read out the state, what is going on, in your material. So there are definitely two directions. First, you can measure it in transport measurement or in the optical measurement. And in terms of the transport measurement, it becomes very important to overcome the problem of the high contact resistance. People are demonstrating, so in order to do the detection in the transport measurement, the contact should be ohmic contact, so you should be able to measure the low, some not very extremely, so in order to measure just the resistance difference, the resistance should be not high. And it turns out in experimental realization that this is very crucial. Well, basically, it is very difficult for us. We tried, let's say, 1.5 years to combine some materials to repeat something in literature, and with the transport measurements, sometimes we're still struggling. So this, for example, here there is a recipe for WSE2, let's say, material that indeed it will work out with ruthenium chloride 3. But we tried different approaches, and it turned out that this is quite problematic. So the transport properties we cannot easily measure. Now we cannot detect the Mott insulator in the transport properties, let's say. But what instead we are doing, we are using the optical measurements in order to see the response from this new situation that are happening. Yeah, so for example, what we were able to realize, this is not our work, it's just explaining that it is happening in the more potential TMDCs. For example, the Wigner crystal, we were able to demonstrate optically that we can reach the Wigner crystal case. So it's a solid phase of electrons moving in a uniform inert neutralizing background that crystallize in the form of lattice if the electron density is less than a critical value. So in the normal words, what happens, you have your twist and you have this Moore potential, which is depicted here. And depending on the gate voltage that you rotate your knob, you can move back and forth the electrons that are appearing there. For example, if the filling factor is 1, you have 1 electron in the Moore potential. Here's the case. And when you have this, these electrons, they try to organize themselves in some crystal structure, and it's called the Wigner crystal. Then you can change your gate voltage, and let's say you go to the filling and 2/3, and you have this filling like this, and then again the electron, the carriers, will recrystallize itself in another type of crystal. And this we were able to, so you change the voltage and you change the configuration of your crystal structure. Yes, you can do it in one device just by changing the voltage on the contacts. And we were able to study this optically. Well, basically what we did, when we reach this Wigner crystal state, we find out that the reflection of the device is changing. So we can see a new bands that appear in the optical reflection spectra. And when we see these new bands that they're appearing, we can say, okay, we reached the Wigner crystal case. Yeah, this is one of the, I will not go to the details. It turns out I'm a lack of time. So, and then you can also, yeah, as I mentioned, this in the holes, these electrons in the potential, they will crystallize, and then there is a Coulomb repulsion between them, and they try to form the crystal. And then you can make either the Wigner crystal or the Mott insulator state. So all of them, they are described by the Hubbard model, and in the Mott insulator case, you have a filling factor around 1, which is formed in the Mars superlattice. And this separation between the electrons, indeed, it is determined by the Moir period. So when you construct your material with defined angle, you achieve the specific Moir period, and then you control this separation between the electrons. And yeah, maybe just one thing to mention, that when people are doing the optical detection, just one slide, I will not go into details. When they do this optical detection, they rely on the fact that there are some specific excitons appearing in these Moir things. So there can be excitons within the layers, and then can be excitons, interlayer excitons between the layers. So it turned out when you have these excitons, when you apply electric field, you have a quantum confined Stark effect, and you can move the wavelengths of your interlayer exciton with your gates. And this interlayer exciton, they serve as a probe for the crystallized state. For example, if you have a Wigner crystal case here, when you probe, you measure your interlayer excitons. Depending when your system is in this case or in this case, the interlayer exciton will feel this difference of this normalization of the crystal structure. And then this interlayer exciton will serve you as a guide, just to prove that something has happened. And then with this detection of the interlayer excitons, one can claim, okay, I have the different filling factor, I have the different state, and maybe it can be described as a Mott insulator, or maybe it can be described as a Wigner crystal. And this is exactly what people published, for example, in 2024 in Nature Physics. The reason why I'm showing this, because we were able to reproduce it already 1 year ago, and we move a bit further with this, but the general concept is like demonstrated here. So you have this image of the interlayer excitons. So interlayer excitons, they have some specific photon energy, so they emit at specific wavelength. And you can, when tuning the gates, as we see here, it's like displacement field or carrier, you can see that the interlayer excitons, they are not just representing some straight light as here. That should be in the case of the quantum confined Stark effect. But in the experiment, there is something weird going on. So there is no linear dependence. There's some abrupt changes of the photoluminescence. And the reason is that there is the exciton-electron interaction that defines the changes. And then you can see, for example, the Mott insulator state, or in the fractional fillings, it's called the generalized Wigner crystal. So, for example, when you see these differences in 1/3 or 2/3, they say, okay, it's from the theory, it turns out it's a generalized Wigner crystal. And if you have the data like this, you are able to publish in Nature Physics. Yeah. So we are very much looking forward. So this, and also we were able to obtain, for example, Mott bosonic insulators. So we improved the optical pumping density, and with this we saw the formation of new excitons, which are called Mott bosonic excitons. So with this, I will just summarize the things. That the advantages of the platform are the following. So we can there is a possibility to create different Hamiltonians. We can control the simulator by the electric field strain, for example, temperature, or using different materials. Those scalability is quite large. So more size is, as we discussed, around 10 nanometers, but can be larger or smaller. And the sizes of the samples are around 5 to 7 microns. But since the area of the study, for example, optically, it's microns, we can have a lot of electrons there, like 10,000 or even more. So we can see what's going on in this large fraction of the device. And then the device operating temperature is around 10 to 40 Kelvin, and the system lifetime is very large. Thank you very much, and I'm looking forward for questions.
Thanks a lot. So it's time for questions. Yeah.
Concerning your photo detectors, yeah, if you have these structures, you probably could expect some sort of specific polarization dependence. And also, well, maybe some sort of dependence on the K, on the wave vector, because you have some sort of kind of result. Is that true?
Thank you very much for your question. It is differently true for the polarization dependence, and this indeed we checked. We measured with linear, circular, and so on, and this is one of the key explanation why we think that. So the dependence on the polarization is one of the key explanation in our case on the mechanism of the photo detection. Yeah, so this we study, and definitely there is a dependence, and depending on which type of detection mechanism you have, the dependence will be different. And regarding the K vector, it's a nice idea, but we did not try it. But we didn't consider this. But in general, it is possible to modify the setup and to measure this case, I think.
All right. Yeah. Thanks a lot.
Thank you very much. Very interesting. What are the possible applications? What is most close to practice? How can it play?
Yeah, perfect question. So I can answer this very long and very short. I decided to demonstrate this example with the photo detector because it is rather close to practicality in terms of that. Indeed, there are photo detectors. Indeed, there are some groups are studying this very precisely, and the advantages of these photo detectors. And the advantages of the photo detectors, for example, based on graphene, are the fact that you can detect in some spectral ranges that are not possible with other alternatives, or there are not so many ways to detect. For example, there works on the terahertz detection with the graphene-based setup, based devices, or near-infrared detection, because graphene can absorb light in different spectral ranges. So it is possible to detect in various. Yeah, it will work. Yeah, it will work in wide spectral range, first of all. And the main advantage there is that it is very fast. The advantages of this type of photodetectors that are fast. Yeah, fast response, because the temperature of electrons, it is increasing very fast, but it can be used in the gigahertz regime because the relaxation is also fast. This is one of the applications, but it's very tough topic because I demonstrate that this physics happens in this that you make with the Scotch tape. When you in real life, if you want to make a production of something, then you need not to use this Scotch tape, but you need to grow it large scale. This is also done, but the physics will not be. I mean, it is there, but what I told you about the Moore potentials and so on, this is quite challenging to implement.
Okay. Yeah.
Sorry.
Good. The next one.
When you show the nice picture, a periodic crystal of electrons, which you call Wigner crystal, I wonder how important is indeed the interaction between the electrons, how large is the R sub S value, and maybe the dominating interaction is the interaction of electrons with substrate periodic potential.
Okay,
How
so
large is the R sub S value?
how large is the R?
R sub s value, which is a dimensional ratio of the purely electron-electron interaction with respect to the kinetic energy.
I think that I tried to demonstrate there was some sort of comparison. Well, first of all, just in general, it's like this. Yeah, hard to answer your question. I tried to demonstrate. So the potential, for example, with a twisted WSE2 is around this value, like 9 millielectron volts, and then there is a tunneling. So it depends. So the tunneling value is like this. So I suppose I did not completely answer your question, but
well, if you cannot, maybe you know the density value, the per
10 to the
square.
12.
How large is
10
the
to the
electron
12.
density?
Electron density.
How-
You.
The number.
I completely out of the. So general, yes. Sorry, I think I missed something. So if you change the in the normal twisted thing, the density is around 10 to the 12th. Okay. Yes.
10 to the 12.
12th. Yes.
So
in the
it's not that-
case, sorry, yeah, it's just of the electrons. Then in the case of the more potential, which I demonstrated here, you have one electron in one potential. Yes, so you have only one them in the potential. Then the size of the more will be like around 10 nanometers between them. So you have one in between 10 nanometers.
Okay. No, then I say that this is not purely Wigner crystal, because this is the major interaction is the interaction of electrons with the periodic substrate potential rather than the interelectron interaction.
All right. So, and maybe the last question that I have, actually, if I may. So, of course, there are magnetic van der Waals materials, and everyone right now, not everyone, but a lot of people are interested in altermagnets. So you would take one layer of magnetic van der Waals material and put another one on top of it.
Twisted by 90 degrees. And then
not necessarily twisted. So even putting one on top of another, you remove the inversion center. So this will be naturally altermagnet. So is it possible to do this? One magnetic van der Waals material on top of another one.
Yeah, it is possible. And why I tell you about this 90 degrees, because I think we discussed this PRL paper maybe already 1.5 years ago, when they demonstrated that due to some specific symmetrical reason, you need to tear it away. You take one monolayer, you can even take one type of material, but you can tear it on parts, and then you should rotate it, and then you put on top of it.
Which materials would you suggest? Specific materials.
Yeah, with magnetic, it's not so straightforward, because the problem is that many of the magnetic materials, they are not very sensitive, stable in the air, first of all, and then the temperatures are quite low when you can reach the limit of the ordering. So it's hard to answer, but we can discuss this. Well, in general, it is possible. We can do everything inside of the glove box, but if you put one on top of each other, it's easy. But if you have to do some this experiment when you tear off one layer on two parts, and then you must need to rotate it vice versa, then it will be very difficult, because you have one side dirty with the spoilers, and then it will be not so.
All right. Yeah. Thank you so much. Anyway.
Thank you.
Yeah. Thanks a lot for the talk.